Hey kids, welcome to section 4.1 Sample Space and Probability. Today we're going to start chapter 4 and we're going to learn all about sample spaces and how to find the probability of an event using either classical probability or empirical probability. So, probability as a general concept can be defined as the chance of an event occurring. Processes such as flipping a coin, rolling a die, or drawing a card from a deck are called probability experiments. Um, so all the different ways that you can, pull a card, flip a coin, draw a green M&M out of a bag of M&Ms. These are all probability experiments. Um, in any experiment, the set of all the possible outcomes is called the sample space. So if we were to down at the bottom, look at tossing a coin, the sample space is heads or tails. Rolling a die, the sample space is 1, 2, 5, 6. So as you can see, the sample space is all of the different outcomes that are possible when you do an experiment. Now, two of the more popular experiments that we talk about in probability and statistics is rolling two die and drawing a card from a deck of cards. So I wanted you to be able to have something visual to look at. You've got all the die on the column and the second die on the row, and you've got all the different combinations of how the two die can end. And then I wanted you to be able to see that there are four different suits in a deck of cards and that there are 13 different cards in each suit. So those are there for you to look back on later. All right, so if we start talking about sample spaces, let's think about when you have children. So find the sample space for the gender of the children if a family has 3 children. Use B for boy and G for girl. Well, when you're talking about children, you could have a boy and a boy and a boy. You could have a boy, and a girl. You could have a boy, a girl, and a boy. You could have a girl, a boy, and a boy. So we got 3 boys, 2 are boys. You could do one is a boy, so boy, girl, girl, um, girl, boy, girl, or girl, girl, boy. And then finally, you could have no boys and have all girls. So there is the sample space if you have a family with 3 children. Another way to find all possible outcomes of a probability experiment is to use a tree diagram. And a tree diagram is where you pretty much have a starting point and you just keep branching off with different possibilities that can happen. So if you used a tree diagram to find all of the sample space for 3 children, you could start with having your first child. Your first child can either be a boy or your first child can be a girl. Then your second child could be a boy and your second child could be a girl, or boy here and girl here. So this is what your tree diagram would look like if you had 2 children. Well, if you had 3 children, you would go one more time, boy, girl, off of each of them. Boy, we'll just abbreviate B and G. So then the different patterns of children that you could have, just follow the branches. So you can stay completely on top, boy, boy, boy. You can do boy, boy, girl. Then you can do boy, girl, boy, and so forth. So you'll see all 8 of the possibilities there. So in many problems, we have to find the probability of 2 or more outcomes. That means that it's necessary to distinguish what's the difference between an outcome and an event. Well, remember, an outcome is what could happen when you perform a probability experiment. An event is all the different outcomes put together of a probability experiment. So you're looking for all the different possible ways and then seeing the probability of something happening. An event with one outcome is called a simple event, like find the probability of getting a 6. A compound event consists of 2 or more outcomes or simple events. So perhaps you're rolling 2 die or you're pulling 3 cards. That would be a compound event. Now, classical probability uses these sample spaces and determines the numerical probability that an event will occur. And it also assumes that all of the events are, or all of the outcomes are equally likely. So everything has a fair shot of being chosen. When you look at the formula for classical probability, you're looking for the number of ways something can happen, the number of outcomes. And then on the bottom, you've got the total number of outcomes in the sample space. So classical probability is really just regular probability, the number of ways it can happen on the top, and the total number of ways something could happen on the bottom. Now, there is a rounding rule for probabilities. It says that it's to 3 decimal places, so that's what we're going to go with. It also says that you can write it as a reduced fraction. So either reduced fraction or 3 decimal places. Find the probability of very first one of getting a red face card when randomly drawing a card from an ordinary deck. Well, there are 4 jacks and 4 queens and 4 kings. So there are 12 face cards in a deck out of 52. No, not 12. Yeah. Hold on. Why is my brain? No, that's right. 4 times 3. Yeah. Um. Oh, but they have to be red. My bad. Sorry. Gosh, I sound really dumb right now. Okay. They have to be red face cards. So there is 2 red jacks, 2 red queens, and 2 red kings. So that's 6 out of 52, which is 3 out of 26, and decimal is 0.115. Sorry, I had a bit of a brain too. All right, if we look at the family having 3 children, remember there were 8 outcomes. We want the probability exactly 2 of the 3 are girls. So remember there were 8 outcomes total. And there was girl, girl, boy, and girl, boy, girl, and boy, girl, girl. So there were 3. So 3 ways you can get exactly 2 being girls, 8 total possibilities. That's 0.375. So basically a 38% chance that you'll have at least, or that you'll have exactly 2 girls. Okay, let's switch over to cards. So if you need to, you can refer back to the chart that had all the different cards on it. In probability theory, it's important to understand the meaning of the words or and. So we're going to talk about them while we do this page and for the rest of the section. A card is drawn from an ordinary deck. Find the probability of getting. So I want the probability that the card I draw is a king. Well, there are 4 kings in a deck of cards out of 52. If we simplify, this gives us 1/13 or 0.077. If we look at the 4 of spades, there is only one 4 of spades out of a deck of 52. So 1/52. Can't simplify, 0.019. It's basically a 2% chance that you'll pick the 4 of spades. All right, probability that you'll pull a face card. So there are 4 jacks, 4 queens, and 4 kings. So that's 12 out of 52. Simplified is 3 out of 13, which is 0.231. The probability of a red card, there are 26 red cards out of 52 total. That's 1/2. That's 0.500. Notice I put extra zeros on to make probability of 3 decimals. The probability that you pull a club, well, there are 13 clubs out of 52. So that's 1/4. So that's 0.250. All right, awesome. Now let's talk about what probability can be equal to. So there's a little chart here that talks about the endpoints, if you will, for probability. Probability can only be between 0 and 1. If something is impossible, it's never going to happen, then the probability of that event occurring is equal to 0. If something is certain to occur, it will for sure occur, then the probability is equal to 1. And basically everything in between is allowed. So, one of the four rules of probability is that the probability of any event E is a number, either as a fraction or a decimal, between and including 0 and 1. So, probability always has to be between 0 and 1, no bigger, no smaller. Number two, the sum of the probabilities of all the outcomes in a sample space is equal to 1. So, that means if I find different probabilities of pulling different cards, if they're all outcomes in the sample space, then they would total 1. Number three, if an event cannot occur, its probability is 0. We just talked about that. And number four, if an event E is certain to occur, then the probability of E is 1. Again, that comes from the fact that the bounds on probability are 0 and 1. So when a single die is rolled, find the probability of getting a 9. Well, you can't get a 9. There is no 9, so the probability is 0. It's not likely to occur. And then letter B, the probability of getting a number less than 7. Well, all the numbers on the die are less than 7, so the probability is equal to 1. Okay, in addition to the other rules of probability, we have something called complementary events. And complementary events says that if the complement of an event E is the set of outcomes in the sample space that are not included in the outcomes of event E, the complement of E is denoted by E bar. So basically, the complement is everything but the outcomes in the sample space. So if I want to find the complement of selecting a month that has 31 days, the complement would be selecting a month that has fewer or not 31 days. So selecting a month that has fewer than 31 days. You could also say that doesn't have 31 days, and that's the same meaning. Letter B, find the complement of selecting a day of the week that begins with the letter T. Well, the complement would be selecting a day of the week that doesn't begin with the letter T. So selecting a day of the week that doesn't start with T. The other thing you could do is list the days of the week that do not start with a T. Letter C, the complement of rolling 2 dice and getting a sum that is an odd number. Well, you could roll 2 dice and get a sum that is even. Rolling 2 dice and getting a sum that is even. You could say rolling a die and getting a sum that is not an odd number, but if it's not odd, then it's even. And then finally, selecting a letter of the alphabet that is used as a vowel or consonant. Well, there's only one letter that can be used as a vowel or a consonant, and that's the letter Y. So the complement would be selecting a letter that's not Y. Selecting a letter other than Y. All right, so we practiced finding the complement so that we can do the upcoming probabilities. The outcomes of an event and the outcomes of the complement make up the entire sample space. That's why it follows that the sum of the probability of an event and the probability of its complement will always equal 1. So right here, the probability of something happening plus the probability of its complement happening always totals 1. You can use Venn diagrams to kind of show complementary events, and we will coming up in a little bit. The next example says, in a study, it was found that 23% of the people surveyed said that vanilla was their favorite flavor of ice cream. If a person is selected at random, find the complement that the person's favorite flavor of ice cream is not vanilla. So if I want to find the probability that their favorite flavor of ice cream is not vanilla, I could do 1 minus the probability that it is vanilla. I know what that value is, so I can do 1 minus 0.23, and I can get 0.770. So when you know the complement, it becomes a lot easier to find the answer. Okay, so now let's move away from classical probability, which remember again is saying that every outcome has an equally likely chance of happening. And let's move on to something called empirical probability. The difference between classical and empirical probability is that classical assumes everything is equally likely outcomes, but empirical probability relies on actual experience to determine the likelihood of outcomes. So, someone has actually performed an experiment and has gotten some data. That's called empirical probability. And we can find that by using the same definition that we've been talking about with probability. We can take the number of ways something happens or the frequency and divide by the total number of ways that something could happen, which is kind of like the total sample space. So, for instance, this question says suppose a researcher for the American Automobile Association asked 50 people who plan to travel over the Thanksgiving holiday how they get to their destination. The results can be categorized in a frequency distribution as shown. Find the probability that a person will travel by airplane over the Thanksgiving holiday. Well, I can find the number of people that say they're going to travel by airplane, that's flying. That's 6. And I can take the frequency 6 and divide by the total frequencies or the total number of people asked, which is 50. So that gives you 3 over 25, which gives you 0.120. So basically 12% of the people are going to travel by airplane. Okay, we keep moving and using empirical probability. This one has to do with blood types. In a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Set up a frequency distribution and find the following probabilities. Okay, so a frequency distribution lists the different outcomes and their corresponding frequencies. So in this case, we have type O blood, there are 21. Type A blood had 22. B blood had 5. And type AB blood had 2. So there's a frequency distribution, lists all the different possible outcomes and their corresponding frequencies. Now we can answer some questions. A person has type O blood. Well, there are 21 out of a total of 50 that have type O blood. So this is 0.420. If I look at the probability that a person has type A or type B, well, there are 21 that have type A and 5 that have type B. So 21 plus 5 over 50. That gives us 26 over 50, which is 13 over 25, which is 0. A or B. Oh, my bad. 22 plus 5, which is 27. It's okay. Which is 27. Yeah, because that's a 2, which gives me, then I can't simplify that. So that gives 0.540. Okay, if we look at the probability that the person has neither type A nor type O, then I can either add the type A and type O's and subtract from 1, or I can find the ones that aren't type A or type O, which means type B or type AB, and add those up. So I can do 5 plus 2 over 50, which is 7 over 50, which is 0.140. Or I could have done 1 minus and then do 21 plus 22 over 50. And you get the same thing. This gives you 7 over 50, which is also 0.140. Either one. A person does not have type AB blood, so I can do 1 minus the probability that he has type AB, which is 2 over 50. That gives me 48 over 50, which is 24 over 25, which is 0.960. Or I could have done all the ones that are not AB. So 21 plus 22 plus 5 over 50. That gives you 48 over 50, which gives you the same thing as before. So however your brain thinks about it is how you should do it. All right, let's look at one more empirical probability. This one has to do with knee replacements. So hospital records indicated that knee replacement patients stayed in the hospital for the number of days shown in the distribution. Find these probabilities. So if a patient stayed exactly 5 days, then I would want the 5, which is 56. It's out of a total of 127. Doesn't simplify, 0.441. If I want the probability a patient stayed fewer than 6 days, then that's going to be 3 and 4 and 5 days added together. I could do that, or I could do 6 and 7 and subtract also from 1. So 3 would be 15, 4 would be 32, 5 would be 56, all out of 127. So that's 103 out of 127, which is 0.811. If I look at a patient stayed at most 4 days, that means 4 days or 3 days or, that's the bottom. So we're looking at just 4 and 3. So that means I've got 15 plus 32 over 127. That's 47 over 127, 0.370. And then finally, a patient stayed at least 5 days. So that's going to be 5 days and 6 days and 7 days added together. So 5 is 56, 6 is 19, 7 is 5, all over 127. That's 80 over 127, which is 0.630. All right, so that's empirical probability, results that come from a specific experience. Now, the law of large numbers talks about probability in a specific way. It says that when a coin is tossed one time, it's common knowledge that the probability of getting ahead is a half. As the number of trials increases, the empirical probability of getting ahead will approach the theoretical probability of a half if, in fact, the coin is fair or balanced. This phenomenon is an example of the law of large numbers. So, as I flip the coin, I create empirical probability. As I continue to flip the coin, I will reach the value of my probability to be the value of what I theorize the probability to be. That's called the law of large numbers. It's not that the number of heads and tails will even out. It just means that the outcome, the probability, is going to tend to go to what the theoretical probability said it should be. Now, the last type of probability that we talk about is called subjective probability. And subjective probability uses a value based on an educated guess or estimate. It's not exact, it's an opinion, it's a guess, it's based on someone's experience and what they think is going to happen. And so subjective probability is what you would anticipate something happening. Like, what are the chances that it's going to rain tomorrow? I would be giving subjective probability because I'm not a weatherman. All right, so here's an application that we're going to talk about. Assume you are at a carnival and decide to play one of the games. You spot a table where a person is flipping a coin, and since you have an understanding of basic probability, you believe that the odds of winning are in your favor. When you get to the table, you find out that all you have to do is to guess which side of the coin will be facing up after it is tossed. You are assured that the coin is fair, meaning that each of the two sides has an equally likely chance of occurring. You think back about what you learned in your statistics class, hint, hint, about probability before you decide what to bet on. Answer the following questions about the coin tossing game. Number one, what is the sample space? Remember, the sample space is just a list of all possible outcomes. So the sample space is the listing of all possible outcomes of the coin toss. So part two asks us to actually list the possible outcomes, and the possible outcomes are heads or tails. There are two possible outcomes, heads or tails. What does the classical approach to probability say about computing probabilities for this type of problem? Well, classical probability says that a fair coin has a 50% chance coming up heads and a 50% chance of coming up tails. So we can say classical probability says that a fair coin has a 50% chance of coming up heads and a 50% chance of coming up tails. Classical probability says that a fair coin has a 50% chance of coming up heads and a 50% chance of coming up tails. Even Steven, equally likely outcomes. So you decide to bet on heads. So we are betting on heads, believing that it has a 50% chance of coming up. A friend of yours who had been playing the game for a while before you got there tells you that heads has come up the last 9 times in a row. You remember the law of large numbers. What is the law of large numbers, and does it change your thoughts about what will occur on the next toss? So remember, the law of large numbers says that as you increase the number of trials, the overall approach is the theoretical probability. So law of large numbers says that as you increase the number of trials, the overall probability approaches the theoretical probability. This means that if you go based on law of large numbers, that everything is going to approach the proper outcomes if you repeat it enough. So this is not going to change your opinion because you know that it's 50-50 shot of coming up as heads. So this does not change your opinion. Number 5 says, what does the empirical approach to probability say about this problem? And could you use it to solve this problem? Well, empirical probability is based on running an experiment and looking at the results. And I can't do that at this time to this problem because I haven't tossed the coin 10 times to know what's going to come up on the 10th flip. So we can say empirical probability is based on running an experiment and looking at the results. Well, I can't use the results because I haven't done them. So this is not able to be used to solve the problem. Number 6, can subjective probabilities be used to help solve this problem? Well, if you think the coin is biased or, unfair in some way, then sure, use subjective probabilities. So, subjective probabilities can be used if you believe the coin is biased. And finally, number 7, assume you could win $1 million if you could guess what the results of the next toss will be. What would you bet on and why? Well, quite frankly, no matter what you bet, it's got a 50% chance of landing on heads and a 50% chance of landing on tails. So it really doesn't matter. Either one has the same probability. 50% heads and 50% tails. So if you want to burn some money, go for it. It's not going to change the outcome. It's still 50-50. All right, kids, if you have any questions, please let me know. And as always, keep calm and keep trucking.